For me. And I'm feeling good.
Hear what I say. We are the business today. Fuck shit is finished today. RT and J.
What is going on, everybody? It's your boy Average Leader here with another video. Today we are tackling Microsoft and Apple's most asked interview question, LRU Cache. This question is also asked by a ton of other companies, including Amazon, Facebook, Bloomberg, and all these other companies. Before we start, if you guys can go ahead and hit that subscribe and like button, that would mean the world to me. It helps my channel out a ton by giving it more exposure to people that don't know me. And if you want to see another problem done, comment down below and I'll make sure to do it for you. With that all out of the way, here we go. So if you were given this in an interview setting and you didn't know what an LRU cache was, hopefully your interviewer would explain it to you. What is an LRU cache? Well, let's start with talking about what cache is. Cache is memory in a computer which stores the most frequently used data. The great thing about cache is that we can retrieve that data very quickly. But one of the reasons we can do this is because cache memory is usually very small and can hold a few pieces of data. So the question becomes, what do I remove to make sure I have my most frequently used data in this finite amount of space? Well, that's where the LRU cache comes in, where we are going to add data into our cache, into our memory, but whenever we go over our cache's capacity, we will remove the least recently used item, hence the name LRU cache. So now that we know that, let's dive into the problem. All right, so we have to design a data structure that follows the constraints of an LRU cache. So let's look at our constructor and method. So we have an LRU cache constructor where we initialize the LRU cache with a positive size capacity. Cool. We have a get method, which returns the value of the key if the key exists, otherwise we return -1, okay. And we have a put method, where we update the value of the key if the key exists, and otherwise we add the key value pair to the cache. If the number of keys exceeds the capacity, we evict the least recently used key. Now, anytime we call put or get on a key, we are using that key. So when it's time to evict a piece of data, or in our case, evict a key value pair, we're just looking for a key such that put or get hasn't been called on it in a while. Another important thing to point out is that we can add as many pieces of data or as many key value pairs as long as that number is less than or equal to the capacity. So between the get and the put method, which one is actually adding new pieces of information? Well, that is the put method, because this is actually adding a key value pair to the cache if it's not already in the cache. The get method, on the other hand, just reorders where an item is within the cache. So it's not really adding new information, it's just reordering information. And I know this sounds like a little confusing right now, but I think it's easier to visualize and see if we work through an example. So let's do that. So I took this example straight out of the question, and we have our inputs right here and our outputs right here. So we start off with the constructor called LRU cache, and we have a 2 inside. So what does this 2 represent? That is the capacity of our LRU cache. So I'm going to make a little visualization. I'm going to make a little container representing our LRU cache, and there's going to be 2 items in this container. And the way I am going to think about this is, let's have 2 sides. On the left-hand side, we'll have the most recently used stuff. And on the right-hand side, we'll have the least recently used items. Cool, so let's move on. Our first call is this put method right here, and we're putting the key value pair 1, 1. So 1 is the most recently used key. It's the most recently used data. Now this cache, I'm just gonna hold keys for right now. Luckily, our key and values are the same, so it's not really gonna matter. But since we just called the put method on the key 1, 1 is the most recently used. So we're going to put 1 right here. Now we're going to move on to this put. We're putting 2, 2. Now 2 is the most recently used key since we just called put on it. So what does that mean? That means 2 goes here and then 1 gets shifted down. So I'm going to actually rewrite this to be a little cleaner. 2 is going to go there. 1 is going to get shifted down. Okay. Now we're going to get 1. Now when we do this, we're calling get on 1. We are using 1. And as we're using 1, we're also making it the most recently used item right now. So Earlier, I was saying that put is the only method where we're actually adding data into our cache. But when we call a get method, we are shifting data around. So in this case, 1 isn't the least recently used item. It becomes the most recently used item. So what I'm going to do is delete it from its spot. I'm going to move it to the front. But now when I do that, 2 gets shifted down to the least recently used. So I'm just going to rewrite this to be 1, 2. Awesome. So 1 is the most recently used and 2 is the least recently used. Okay, cool. So moving on. So now we put 3 into our cache. 3, we call the put method on 3. So 3 becomes the most recently used. So now we put 3 in our cache. And while we do that, we notice that there are 3 pieces of information in our cache, but the capacity, as noted before, is 2. So what happens? Well, we're given instruction that if the number of keys exceeds the capacity from the put operation, we need to evict the least recently used key. And what is the least recently used key? Well, that is 2 in our situation. So I'm going to remove 2, and I'm going to shift everything down. Okay, so 3 is going to be here, 1 is going to go here. So 3 is the most recently used, and 1 is the least recently used. Cool. Now, and also, while I evict 2, I'm going to have a little eviction pool. So we know exactly where 2 is. 2 is evicted, it's in the eviction pool. We don't want to be in there. So now we're going to get 2. Well, 2 isn't in our cache, and we're given instruction that if it's not in our cache, then we need to return -1. So that's exactly what happens here. Now we're going to put 4. So when we put 4, what happens? Well, the size is greater than the capacity. There's 3 elements in our cache, but we can only have a capacity of 2. So what happens? We evict the least recently used key. And in our case, the least recently used key is 1. So I'm going to take 1 out, put it into the eviction pool so we don't forget. And now 4 becomes the most recently used, and 3 becomes the least recently used. So I'm going to shift this down so it looks a little cleaner. Okay, cool. So 4 is done. Now we're going to get 1. Well, 1 isn't in our cache, it's in our eviction pool, so that's why we return -1. Then we get 3. Since 3 is in our cache, we're going to return the value of 3, and in our case, since the value was the same as the key, we return 3 here, and we do the same thing with 4. As we get 4, 4 is also in our cache, so we're going to return the value associated with the key 4. Okay, cool. So now we know how an LRU cache works. We've done an example to clarify some questions we might have had. So the real question is, how can we build an LRU cache using some data structures? Well, off the bat, this is screaming, use a hash map. And why is that? Well, we have all these put and get methods, and like a hash map uses both of these methods. And not only that, we're putting key value pairs and we're getting a key. And while we call get on that key, we're returning the value. So that is exactly what a hash map does. It's one of the many functionalities that a hash map has. So off the bat, we're going to use a hash map. And for right now, we will let our key value pair both be integers. Okay, dope. Now, the harder part here is thinking of a data structure that acts as our container or acts as our cache. We need a container that can accomplish 3 things, namely being, 1, we want some way where we can order our most recently used items coming in one direction and our least recently used items leaving in the other direction. 2, we want our add and our evict method to be all of 1. Because remember, every time we called the put method, we would put our key value pair in the front, in the most recently used side, and we would evict our key from the least recently used side. So we need to add and evict in O of 1 time complexity at all times. 3, we need to access anything in the middle of our cache. Let's say we were given a certain situation where we had a cache like this, where most recently used is on the left-hand side and the least recently used is on the right-hand side. And our capacity is 4 in this situation, and we call get 3. Now remember, what did we do before? All we did was move 3 to the front and shift everything else down. So our cache looked like this. But we need to access this also in O of 1 time somehow. So how can we do this? Well, when I'm in a situation where I don't exactly know what to do, I list all the data structures I can think of that somewhat pertain to what we're doing. So we need a data structure that can act as a container. So off the bat, I'm thinking we have array, we have array list, we have linked list. We can use a stack as a container, queue as a container. And you know what? Let's just start with this. But we can also use hash sets, we can use a deck, and maybe a few others that I'm not naming right now. But now let's think about why one could work or why one couldn't work. Once again, these are the three criteria that we're going to use to judge each of our data structures. So let's start with an array. Well, let's see. Can we get this ordering where we have the most recently used items on the left and the least recently used items on the right? Yeah, I'm sure we can figure out a way to do that. Sure. Is our add and our evict an all of one? Well, that's where it's tricky, because our add, we're always going to be adding to the front, but let's just say there were items in our array and we were going to add to the front. When we do that, we need to shift everything else down one to make space for this one. So that's an O of n time, not an O of one time. So we can cross that out. Array, not going to be used. Now let's think of an array list. Well, an array list is backed by an array, and it actually has the same problem, where if we, once again, had items in our array list and we want to put something in the front, we have to shift everything else down to make space for that one. So that also is an O of n time. So we don't want an array list. Now, linked list. Okay, can we get this ordering where the most recently used items are on the left and the least recently used items are on the right? I'm sure we can get something like that. Why not? Can we add elements to the front in O of one time? Well, yes. As long as we have a head, we can add elements to the front in O of one time. And can we remove or evict elements in O of one time? Well, if we used this current linked list, it's called a singly linked list because all the arrows go in one way. We would have to iterate through this entire linked list to get to the end, and that will be an O of n time. But is there a quick change we can make in order to access the last node? Well, yes, we can make this a doubly linked list where we'll have arrows going forward and backwards. And by doing that, we can also have a tail node, and as long as there's a tail node, we can evict the last node in our linked list in O of one time. Now, can we access anything in the middle? So that is where it's going to be tricky. Because currently, to get to this middle node, we can either use the head or the tail to iterate to the middle. But is there a way where we can somehow get access to that node in O of one time? Well, we currently are utilizing a hash map. And our key is an integer and our value is an integer. But if that key could somehow map to a node containing that value, then we could have access to all our nodes in O of one time. So what I'm proposing here is our hash map can have the keys being integers and our value be nodes. And as long as that key maps to that node, we can easily have access to the node that we're looking for. And if we have access to the node, we also have access to the pointers. And if we do that, we can quickly remove that current node out of the linked list and also move it to the front in O of one time. So that looks like it's a good idea. It looks like it's checking out all our criteria. And for the sake of just showing that the other data structures really wouldn't work, I'm just going to go to stack. So stack, in my opinion, I think a queue makes more sense than a stack, because let's say that we put each element one time and we didn't update any values. That means the first value we put would be the least recently used item. Let's say we put 4, then put 3, then put 2, then put 1. Well, 4 is the least recently used item. So we'd want that FIFO ordering, and the stack doesn't provide that. So boom, stack is out of the equation. But now with the queue, queue luckily has this ordering that we're kind of looking for, and the add and the evict are also O of 1. However, it's hard to access stuff in the middle using a queue, so that's why that wouldn't work. So all roads lead to this doubly linked list hash map combination. And that is exactly what we are going to do. So let's go ahead and code that. All right, so let's just remind ourselves that we are going to use a hash map where our key is the integer, and then our value will be a node containing, oops, if I could spell, the node containing the value of the key. And we need a doubly linked list. So first things first, let's make a node class, because linked list is made up of nodes. Let's just go ahead and make our node class. And we can do that by making a private inner class. We'll call it node. And in the node class, what are our variables that we want? Well, I think we'd want our key and our value in our node, because when we evict something from our hash map that we'll eventually make, we're going to need access to the key, and our tail is going to be pointing to our last node in our cache. So we're going to need this key, because this is what we're going to ultimately remove from our hash map. And we are going to want a next and a previous pointer. So I'll make it node next, node prev. Okay, so that's going to be our inner class. Very easy, straightforward. And now next, like I said earlier, we're going to need to create a hash map. So I'm going to make a hash map. I'll call it map. And our key is going to be an integer, which will represent our key, like the key that we're putting, this key right here. And our value will be a node. And we'll just call this map. And we're also going to need a head and a tail node. And finally, we need capacity, which can be seen from all of these methods. So let's go ahead and make capacity global out here. So in our LRU cache, when we're initializing everything, let's go ahead and initialize our hash map. And let's initialize our capacity. Let's go capacity. Remember, that capacity is referring to this capacity, and this capacity, the capacity on the right-hand side of the equal sign, is referring to the capacity that's passed in. And we're going to initialize our head, and we're going to initialize our tail. Oops. And finally, to make this a linked list, all we have to do is set the head's next pointer equal to the tail, and the tail's previous pointer equal to the head. All right, so in this one constructor, we have made our doubly linked list with all this code right here, and we've also initialized our hash map. So awesome, we're off to a great start. And let's make a method which will allow us to add nodes to the front of our linked list. So that would look something like this. I'll call it add to front, and it will take in a node, because eventually we're going to only add nodes to the front of our doubly linked list. And this is just pretty straightforward code. The first thing we'll do is grab whatever the head's next is pointing to. So I'll just call it head next, and that'll be head.next. So what we're going to do is set our node that we're passing in next to this head next. And that would look something like this. All right. And to make sure that we have pointers going both in the forward direction and the backward direction, we would also set the head next, its previous pointer pointing to our node that we're passing in. All right. And finally, we would need to reassign the head. We'd have to reset whatever the head's pointing to our current node. So what we can do is we can just do head.next equals n, and finally n.prev equals head. So this way we have successfully added everything to the front of our linked list. And next, let's just make a generic remove method. So that would look something like this. And in our remove method, it would be easy, because all we'd have to do is get the passed in nodes, next node and previous node. So let me go ahead and do that. Next node equals n.next, and then node prev node equals n.prev. And we would just set the previous nodes next to the next node, and the next nodes previous to the previous node, to the prev node in this case. And that way we'd completely remove the node that's passed in out of our linked list. So by just doing next node dot next, dot prev equals prev node, and then prev node dot next equals next node, we have successfully removed that node out of the doubly linked list. So awesome. Now that we have those out of the way, we can actually go into our puts and our get. So let's start with the put method. So in our instructions, we're told that we'll update the value of the key if the key exists. So if our key is in our map, all we have to do is update that value. So let's just do that quick check. If map.contains key, let's go ahead and update its value. So first we need to grab the node that is associated with that key. So that would look like node, old node equals map.getKey. And after we do that, we're just going to change that node's value to the value that's passed in. And then we would put this node back into our mapping. So map.put old node. Now, since we called put on this key, we technically use that key. So this key is the most recently used item that we just used. So let's go ahead and remove it from where it is in our cache, and we're going to add it to the front. So I'm going to do remove old node, and we'll call the add to front method on old node. And okay, cool. So that should work if our map contains the key. Now, otherwise, if it doesn't contain the key, that means we need to add the key value pair to the cache. So let's go ahead and we'd have to make a new node. So node, new node equals new node. And I'm going to set this new node's key and value to the key and value that's passed in equals key new node dot value, or val rather, because I think that's what we named it. Oh no, it is value. Oh, I really hope I didn't mess anything else up. Value, okay, equals value, sorry about that. And let's go ahead and put this key value pairing in our map. So map.put key new node. Awesome. And whenever we do that, remember, so since we just used this, this becomes our most recently used item. So we're going to add this to the front of our doubly linked list. So we're going to do add to front new node. Okay. Now, once we add to front, what is the one thing we need to check? We need to check if the number of keys exceeds the capacity. So how do we know if the number of keys exceeds our capacity? Well, luckily we have this capacity variable up top, so we have access to that at all times. Okay, so how can we check to see if the size of our cache is greater than our capacity? Well, our mapping contains all our key value pairs, so let's just check to see if the size of that map is always less than or equal to our capacity. Or in other words, if the map.size is greater than our capacity, what does that mean? We need to evict. We need to remove the last item in our doubly linked list. Or in other words, we're going to remove the least recently used item. This is why the tail pointer comes in really handy, because all we'd have to do is remove our node, remove that node out of the doubly linked list, and we'd also have to remove the key value pairing from our map, from our hash map. So all we have to do is grab the node that the tail node is pointing to. So prev tail equals tail.prev. And we would remove the key that this prev tail holds from the mapping. So map.remove prev tail.key. And finally, we'd remove it from the linked list. So let's go ahead and remove prev tail. So awesome. I think this is the put method. Now let's go into the get method. I think it's a little bit more friendly. So luckily, all our key value pairings are in our mapping. And if we did this properly, then we will remove properly from our mapping. So all we'd have to do is check to see if our map, our hash map, contains that key. And if it does, we just return that value. So if map.contains key, because this key is the one that's passed in, let's go ahead and grab that value. So remember, the value in our hash map is a node. So let's just grab node, and I'll just call it return or ret equals map.getKey. Remember, when we call the get method on our key, we need to remove where it currently is in our cache and move it to the front because that becomes the most recently used item now. So let's go ahead and remove ret, and let's add to front ret. And finally, let's go ahead and return this this node's value. So return ret.val. And otherwise, if the map doesn't contain the key, we're going to have to return -1. And yeah, guys, I think that's how you do this. So hopefully this works.
They ask you how you are, you just have to say that you're fine when you're not really fine.
Dang it. Value. My bad. I keep calling it val. My bad.
You just can't get into it because they would never understand.
Dang it. Oh, right. It's not map.contains. It is map.contains key. So wherever that sucker is, it contains key, since it's a hash map.
Because they.
All right. So another mistake has been made, ladies and gentlemen. Where is this thing? All right, guys. I'm so sorry. Obviously, we need to put both the key and the value pair. Oh, right. We need to put key and the old node value. My bad. All right, and bingo. All right, after three little errors, we got an accepted answer. So let's submit this. Hopefully, this works for everything else. And awesome, we did it. This was a lot of code, guys. Okay, so let's talk about runtime. Well, luckily, everything is O of 1. We ensured that, right? Because our add to front is O of 1, remove is O of 1. Our runtime for everything is O of 1. But now, although we do a great job with our time complexity, we are definitely utilizing a good amount of space here. But at the end of the day, our cache is only holding what our capacity is. So our space complexity is O of the capacity that is passed in. I really hope that helped. Please give this a big like and subscribe to the channel. Also, if you want me to do any other problems, go ahead and comment down below and I'll make sure to do them. And yeah, guys, you guys have a great rest of the day. I'll see you
We
guys
are the
later.
business today. Fuck shit is finished today. RT and J, we the new PB&J. We dropped the classic today. We did a tablet of acid today. The joints with the matches and actions away. We dash away. Donna and Dixon, the pistol is blasting away.
Doctors of death, killing our patients of breath. We are the pain you can trust. Crooked it works, hooking up curses and slurs. Smoking my brain in a mush. I became famous for flaming you.